Hello friends, I welcome you in lecture number 36 on group theory. In this lecture also we will discuss one more question on group theory which was asked in GTU Summer 2021 exam for 7 marks. Here question is about proving that given set is a group with respect to binary operation multiplication modulo 7. Now set is having 6 elements 1, 2, 3, 4, 5 and 6. So this is a finite set and we have to prove that this G is an abelian group of order 6 with respect to multiplication modulo 7. So this is modulo group, as we have discussed in some of the previous lectures also, that whenever our operation is multiplication modulo or addition modulo, the set is not having integer as its elements. Here 1, 2, 3, 4, 5, 6 are not considered as integers. Instead of integers we are having equivalence classes generated by 1, 2, 3, 4, 5 and 6. So our set is this set of equivalence classes, and on this set we are given the binary operation multiplication modulo 7. So we recall the definition of multiplication modulo. If I consider two equivalence classes generated by A and B, then this is equal to product of A and B modulo 7. So AB modulo 7 means we have to decide the remainder when this product A into B is divided by 7. So this is the equivalence class generated by remainder when A into B is divided by 7, and this is true for all AB equal to 1, 2, 3, 4, 5 and 6. So first you must be clear that your set is not this set of 6 integers. Instead of integers, elements are equivalence classes, but some authors are using simply this notation 1, 2, 3, 4, 5, 6. So they can ask you in this way also, as they have asked in this GTU Summer 2021 exam. So remember, whenever we have addition modulo or multiplication modulo, given set is the set of equivalence classes generated by given integers. Here integers are 1, 2, 3, 4, 5 and 6. Now we want to prove that this is an abelian group. Now we observe that there are 6 elements only, so this set is finite set and its order is 6. Order of a group means number of elements in the group. So this is a finite set and we will show that it is an abelian group. So we want to prove that this is an abelian group, and for that first we have to show that it is a group. Now because we are having finite number of elements, we can first prepare the composition table for this set, for this binary operation multiplication modulo 7. And to prepare the composition table, we remember this definition of multiplication modulo. A multiplication modulo 7 B equal to remainder when A into B is divided by 7. For example, if I am interested in 3 multiplication modulo 4, then this is equal to 3 into 4, that is 12 modulo 7. That means I have to find out the remainder when 12 is divided by 7. So we know this. So here we have remainder equal to 5. Therefore 3 and 4 when operated by multiplication modulo 7 will give us 5. Similarly, suppose I am interested in multiplication modulo 4 between 4 and 5. So product is going to be 20. 4 into 5 modulo 7, and we find out the remainder when 20 is divided by 7. So this is 7 into 2, 14, and remainder will be 6, so this will give me 6. And whenever our product is less than 7, for example, if I consider 2 multiplication modulo 7 3, then I have 6, and 6 modulo 7 will give me 6. So 6, when we divide 6 by 7, we understand in this way: 7 into 0 is 0, 6 minus 0 is 6, so remainder is 6. So whenever this product A into B is less than 7, we will write it as it is. So for 1, 2, 3, 4, 5, 6, whenever we have integers which are less than 7, we will write this is equal to 1, 2, 3, 4, 5, 6. That is 1 modulo 7 equal to 1, 2 modulo 7 equal to 2, 3 modulo 7 equal to 3, and so on up to 6. And whenever this product is bigger than 7, we will divide it by 7 and we will write down the remainder. For example, we can go for 5 into 6. 5 multiplication modulo 7 into 6, that is 30 modulo 7. So we find out the remainder when 30 is divided by 7. So I have to write 7 into 4, that is 28, and remainder is 2. So here I will write 2 because remainder is 2 when 30 is divided by 7. So using this definition of this multiplication modulo 7, I have prepared first the composition table. First I have written the given set, then I have written the definition of multiplication modulo 7. A multiplication modulo B equal to AB modulo 7, that is remainder when A into B is divided by 7 for all AB belongs to G. And then I have prepared the composition table. So here I have written 1, 2, 3, 4, 5, 6, here 1, 2, 3, 4, 5, 6. Here I write the corresponding operation, which is multiplication modulo 7 here. Then I start with first element. I take 1 into 1, 1 into 2, 1 into 3, and so on up to 6. And we observe that 1 into 1 is 1 because 1 is less than 7. So I will write directly 1. 1 into 2 is 2 and 2 is less than, so I have written directly 2, and so on up to 6. Then for 2, 2 into 1, that is 2, it is less than 7, so I keep 2 as it is. 2 into 2 is 4, it is also less than 7. 2 into 3 6, it is also less than 7. Then 2 into 4, that is 8, and it is bigger than 7, so I have to decide the remainder when 8 is divided by 7 and remainder is 1, therefore I have written 1 here. After that 2 into 5, that is 10, 2 into 5 10, and I divide 10 by 7, so remainder will be 3, that I have written here. Then 2 into 6 is 12, 12 divided by 7 will give me remainder 5, so here I write 5. So in this way I have written all the entries in the composition table. For example, this 5 into 5, that is 25, so we have to find out the remainder when 25 is divided by 7. So we have 7 into 3 21, 5 minus 1 is 4, so here I have written 4. So in this way we have to prepare the composition table, and we have to write in this way systematic entries systematically in the composition table. You don't have to show all these things, this is just for understanding. Now once we prepare the composition table, then we can start verifying, or we can start proving all the properties. It is already given that this G is a group under multiplication modulo 7. We have to prove it. So we already know that G is a group and we want to prove it. For that, we are already sure that all the properties must be satisfied. So first property is this given set G must be closed under multiplication modulo 7, that is closure property. That means if I take any two elements in group G, then A multiplication modulo 7B must also be in G. So this we can observe from the table. We can observe all the entries in the table, and we find that all the entries in the table are also in given set G. Therefore this closure property is satisfied. So first I have written this closure property. From the table it is clear that A multiplication modulo 7B belongs to G for any AB belongs to G. Therefore G is closed under multiplication modulo 7. Now second property is associative property. So for associative property, we recall that we have to prove that if we take any three elements A, B, C out of this 1 to 6, then we must have these two equal. A multiplication modulo 7, B here multiplication modulo 7C. So now there are so many different possibilities for A, B and C, but we will not check for all those because we will require more time. Okay, that will be time consuming process to check for all possible values of A, B and C. But here we are sure that associative property must be satisfied because the question is prove that given set is an abelian group. So we can check randomly for any three elements. Suppose I want to check for 2, 3 and 6. Suppose I consider A equal to 2, B equal to 3 and C equal to 6 in the given set. Then I first find out this quantity, okay, that we can easily find from the table. I consider 3 and 6 in the bracket, I keep 2 outside. So first I find out what is 3 into 6 under this operation multiplication modulo 7. So here I have 3, here I have 6, and 3 multiplication modulo 7, 6 will give us 4. So here I write 4, this I replace by 4. Then I have to find out this for 2 and 4. So if I take 2 here, here I take 4, then here I have 1. So I obtain by considering 3 and 6 in one bracket, I obtain my answer as 1. Now I change this grouping, I consider 2 and 3 in the bracket and I keep 6 outside. So first I decide what is 2 into 3. Here we have 2, here it is 3. So this is going to be 6 and 6 multiplication modulo 6. So here I have 6, here I have 6 here, and we find that 6 multiplication modulo 7, 6 is also 1. So we can see these two are equal. Now this is true for all possible combinations of A, B and C, and we will not check for each and every possible combination. We will directly write that it is clear from the table that this property is satisfied. So here I have written clearly A multiplication modulo 7, B multiplication modulo 7C equal to, then we consider A and B in the group, C outside for any A, B, C belongs to G. And this we can mention that from the table we have this, clearly we have this, therefore associative property is satisfied. Now next one is existence of identity element. So we recall the definition of identity element. Identity element is that element in the given set denoted by E such that if we consider this binary operation with any other element of group G, then we must get that element back. So this must be equal to A for all elements in the given set, and this E must be unique. we have to show the existence of unique element in a given set such that this property is satisfied. A into E equal to E into A equal to A. So out of this 1, 2, 3, 4, 5, 6, which element will work as identity element, that we want to decide. So if you recall, in some of the previous lectures I have shown you the trick for deciding identity element. So for that we look for the row identical to this row, and that we look for this row in the composition table. So you can observe the row identical to this row in the composition table is first row. This row is identical to this 1, 2, 3, 4, 5, 6, and here we have to find out the column which is identical to this column. So that we observe here. Okay, here we have 1, 2, 3, 4, 5, 6, and if you recall, we have seen this method, and then we find out the point of intersection of this row and this column, and at the intersection entry is 1, therefore 1 is the identity element. Or we can directly check also. We can see 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3, 1 into 4 is 4, 1 into 5 is 5, 1 into 6 is 6, and the reverse thing is also true. So 1 into 1 is 1, 1 into 2 is 2, 1 into 3 is 3, 1 into 4 is 4, 1 into 5 is 5, 1 into 6 is 6. And similarly we can check in reverse way. 2 into 1 is 2, 3 into 1 is 3, 4 into 1 is 4, 5 into 1 is 5, and 6 into 1 is 6. Therefore 1 is the identity with respect to multiplication modulo 7. So we can write in this way. From the table we find that 1 into A equal to A into 1 equal to A for all A equal to 1, 2, 3, 4, 5, 6 in given set G. Therefore 1 is the identity of G with respect to multiplication modulo 7. Therefore identity exists in the given set with respect to our operation. Last property for group is existence of inverses for each element. So we can recall the definition of inverse. If you recall, suppose I have some element A in a given set, and if I can find out another element from the same set, say B, such that A into B equal to B into A equal to identity element, here identity is 1, then this A and B are called inverses of each other. So to find out inverse for each element, we will start from the first row, and we will search for identity element in this row. For 1 we will search in this row for the identity element. So at the very first place we obtain 1. This means 1 multiplication modulo 7 with itself equal to 1. Therefore 1 is self inverse, or inverse of 1 is 1 itself. To check for inverse of 2, we search in this row and we look for identity element in this row, and here we find out 1. So here I can write that 2 multiplication modulo 7 4 equal to 1, and let me cross check for this also. So if I check for 4 and then I find out identity here, this means 4 into 2 equal to 1. So here we have 4 into 2 equal to 1. This means 2 and 4 are inverses of each other. Same thing for 3, we search for identity in this row. So here I get identity. So 3 into 5 or 3 multiplication modulo 7 5 is 1, and we check for 5 also. So here we obtain 1, that means 5 into 3 equal to 1. So this is equal to 5 into 3 also. Therefore 3 and 5 are inverses of each other. And last, for 6, we search in this row, and here we obtain 1, that means 6 multiplication modulo 7 6 equal to 1. Therefore 6 is self inverse. So we observe that every element of given set G has inverse in G. So that we have written here systematically existence of inverses. From the table we find that 1 into 1 is 1, therefore 1 is self inverse. 2 into 4 and 4 into 2 equal to 1, therefore 2 and 4 are inverses of each other. Similarly 3 and 5 are inverses of each other, and 6 is self inverse. So we have verified all the properties for given set to be a group under given binary operation. Therefore given set G is a group under multiplication modulo 7, or we can directly write that G with multiplication modulo 7 is a group. Now we are asked to prove that G is abelian group. So we have to check property for abelian group also, that is we have to check commutative property, and we are familiar with commutative property also. If A star B equal to B star A for every element in a given set, then commutative property is satisfied. So now I have to check for commutative property for this, and you can see there are so many possible values for A and B here. So it is time consuming to check for every possible value of A and B. Instead of that, if you recall, whenever we are discussing composition tables, we can decide from the table also whether given set is abelian group or not. So for that we have to first draw the main diagonal here. So if you observe, I am drawing the main diagonal. Let me draw this first. Now I draw the main diagonal. So I start from this, and I draw the main diagonal. Now if you recall that if entries are symmetrical with respect to main diagonal, then our set is an abelian group. So here we have first drawn the main diagonal. Now we will check whether entries are symmetric with respect to main diagonal. So we start from this. Here you can see, here I have 2 and 2. So here entries are symmetric with respect to main diagonal. Now we check for this. Here I have 4 and here I have 3 and 3. So here also you can check these are symmetric with respect to main diagonal. Here I have 6, then 6 here, 4 and 4. So this is true for this also. So in this way we have to check. Here I have 1, so here 1, then 5 and 5. So if we draw the line perpendicular to this main diagonal, then we can see entries are symmetric with respect to main diagonal. Similarly you can observe here 3, 6, 5, and here also 5, 3 and 6. Then 1, 5, 1, 5 here. So you don't have to draw all these type of lines. I am just drawing to explain that these entries are symmetric with respect to main diagonal. Then here I have 3 below 4 and above 4. So all the entries in the table are symmetric with respect to main diagonal. Therefore given set is an abelian group. So if this property is satisfied, that all the entries in the composition table are symmetric with respect to main diagonal, then our set is always abelian. And you can check, for example, suppose I consider 3 and say 4, then here I get 5, that is 3 multiplication modulo 7 4 equal to 5. So I must have 4 into 3 equal to 5, so that I can check here 4 into 3 and I obtain 5. So if entries are symmetric with respect to main diagonal, then this property will automatically be satisfied. So from the table we can write that commutative property is also satisfied because entries are symmetric with respect to main diagonal. Entries in the table are symmetric with respect to main diagonal. This means AB equal to B into A for all AB belongs to G. Therefore G is abelian group, or G is a commutative group. Another word for abelian group is commutative group, because commutative property is satisfied. So G is abelian or commutative group. So hence we have shown that G is an abelian group, and because G has 6 elements, it is an abelian group of order 6. So they can ask you this type of questions. This is very easy question. You just have to remember the definition of multiplication modulo 7, and then you have to first prepare the composition table, and using composition table you can decide all the properties whether they are satisfied or not. So I hope you understand this lecture. If you have any questions, you can ask in the comment section.